Hello everyone, my name is Yatin Gupta and I welcome you all to my channel W Concepts. So, in today's lecture, we are going to cover the part 7 of Basics of Network Theory, and today I'm going to talk about nodal analysis. In nodal analysis, we will first discuss about the procedure apply nodal in any given circuit, and after completing this, we will discuss some key concepts that you can use while solving any circuits. So let's begin today's lecture. Okay, procedure to apply nodal on a circuit. The first step here is identifying the essential nodes. Essential nodes are the points where three or more components are connected together. So let us understand this with a given circuit. Okay, so in this circuit, we will first need to find out which nodes are the essential nodes. Now, if you see, I have drawn V1 and V2 at these two nodes. Now, these are the only two nodes that have exactly three components connected to them. There can be more than three, but in this particular situation, we have three components. For V1, it is 20 ohms, 50 ohms, and 10 ohms. And for V2, this is 10 ohms, 50 ohms, and this 10 volts of voltage source. So these are our essential nodes. And the second point here is choose a reference node, which is usually the ground potential node, as your point of reference. We will have to choose a reference point for our circuits in order to solve this. So here, these two nodes I'm taking as my reference node, which is the ground potential. These are actually not two nodes. This is a single node only, as they are shorted together here. So we will count them as one node only. Okay. Now in the second step, we apply the Kirchhoff current law. That means KCL at each node. Now what KCL states? KCL states that all the currents that are either coming out or coming into the node, the sum of all of them is equal to zero. So what we will do, we will write down all the currents that are coming out of each node. Okay. So as you can see for this V1 node here, I have drawn three currents that are going in outward with respect to the V1. Always consider that whenever you are drawing the current for a certain node while applying the nodal analysis, always draw the current coming out of the node. Never do it like this, that one node is going out, the one current is going out and then other current is going in. You should always consider all the currents coming out of the node. Even if the taken direction is wrong from your end, it will come out as a negative value. Let's just say I have taken I3 as a wrong direction. It should be from V2 to V1. So the value of I3 will come out as negative. That means it will be from V2 to V1 only. Okay. Now similarly, for V2 node also, you will do the same thing. You will assume three currents which are coming out of the V2 node like this: I4, I5, and I6. So this is the second step here. Now, for each essential nodes, excluding the reference node, you will not include the reference node here. You will only include the essential node. The sum of currents coming out should be equal to zero. That means for V1 node, I1 plus I2 plus I3 should be equal to zero. And for V2, I4 plus I5 plus I6 equal to zero. Okay. Now, what we will do, we will write down the equations for each current that is coming out of V1 node here. Now we need to calculate the value of V1 and V2 here. So we will apply the KCL for both the nodes here. Okay, I3 plus I1 plus I2 equal to 0. So what is I3 here? I3 is basically the current which is coming out from V1 and going towards V2 here. So in this case, if it is going from V1 to V2, we have already assumed that V1 is at higher potential. So we will write V1 minus V2 by 50 here for I3. And I1 will be V1 minus 5 divided by 20, the potential difference divided by the resistance. And I2 will be V1 divided by 10 equals to 0. Now, if we can find out the value of V2 here, we can directly calculate the value of V1. Now, in this particular circuit, the value of V2 is directly known to us, and that is equal to 10 volts. How? This is the ground potential, right? So the potential here will be 0. And now if I go from this point to V2, if in this direction from this path, the only component that I can see here is 10 volts. Now it is either in the supporting polarity or the opposing polarity. I will discuss about this supporting and opposing polarity in the upcoming slides. So now currently it is in the supporting polarity because we are going from minus to plus here. So we will add 10 volts and then we will reach V2. So V2 is basically at 10 volts potential. Now after putting the value of V2 in this equation, 10 volts, V1 will come out as 2.64 volts. Okay, so this is how we can calculate the node voltage of any given circuit using the nodal analysis. Okay, now the number of equations required to solve a network using nodal analysis can be calculated by En equals to n minus 1. Now, what is n here? N is basically number of nodes in any given circuit. Now, while writing the value of this n here, you should consider following things. While counting the total number of nodes, we have to consider the reference node as well. Now, as you know that there are essential nodes and then there is a reference node as well. So if you're counting the value of n, count all the essential nodes and also count the reference node as well. The second thing that you should remember while using this equation is that the value of voltage at any node is already given to you. Do not consider that node in the calculation of number of nodal equations. There might be a situation that a node voltage value is already known to you, like in the circuit that we already solved just now. The V2 was already known to us. So we will not consider V2 in our N value. Okay. So this is the second thing that you should remember while applying this equation. Now, let us discuss about some key concepts. Okay, now as you can see, there are four different scenarios, and in all the four different scenarios, the potential difference that is coming out here is equal to 5 volts only. Now, sometimes there is a confusion while solving circuits in these kind of situations. So, let me explain this. Always use the higher potential minus lower potential phenomena. As you can see, this node voltage is VA here and this is VB here, and the potential difference here is 5 volts. Now this is the plus potential, that means the higher potential, and this is the lower potential here. So you will always write the voltage value first at higher potential and then subtract the lower potential value from that. So that is going to be VA minus VB, that is going to be 5 volt. In the second case as well, this node is at 7 volts, it is at higher potential, and this is at 2 volts. So you will always write 7 minus 2, that is 5 volts only. In the third case also, this is higher potential, so this is minus 1 minus of minus 6, that is again going to come out as 5 volt only. And in the fourth case as well, this is 5 minus 0, again 5 volts. Now, pay attention to this circuit here. This is point P and this is point Q. Now, the potential of point P is Vp, the potential of point Q is Vq, and I have drawn two currents here. The direction is opposite to each other. This is IPQ. That means the direction of current is from P to Q. So if I have assumed that the direction of current is from P to Q, I have already assumed that the potential at P point is higher than potential at VQ, because in that case only the current can flow from P to Q. So I'm always going to write higher potential minus lower potential. So this is Vp minus Vq divided by R. This potential, this resistance value here is R. Let us just assume that. So that is going to be equal to IPQ. Now if we take the other case, IQP, and this is the direction, that means the direction of current is from Q to P. So I have assumed that the potential of Q is greater than potential of P. So in that case, I'm going to write IQP as VQ minus VP divided by R. Okay, so this is the one thing that I was talking about while we were doing the procedure for the nodal analysis. While going from one point to the other in any given circuit, you might find some components in between. like this voltage source here. Now this can be either in the supporting polarity or in the opposing polarity. So how would you know that it is supporting or opposing? Here you can see the direction of current is like this from Q to P. Okay. And this is the direction here. Now, if the current is entering the negative point of the component, so you're going from basically negative to positive. Yeah, that means something is adding up here. Some potential is adding up here. So you will write plus E here. So it is adding some potential, right? So it is in the supporting polarity. Where in this case, when you're writing the equation for IPQ, it is going inside the positive terminal of this component. So you're going from positive to negative. That means something is getting subtracted, some potential is getting subtracted. So here you will write minus A. So that is why this component here is in opposing polarity. So these are some key concepts that I thought you could use while you're solving any circuit. Okay, so that's all for this lecture. I will see you in the next one.